Hello again with another episode chapter from Aquarius tutorial. So in chapter 3, we have introduced the origins of the geometric Brownian motion differential equation, which describes how the stocks move, which is this differential equation. And today we are going to continue this and introduce the solution of this equation. So you start at some point in time 0, you move forward in time, and at some moment t, what is the value of the stock price? So Wikipedia shows the derivation of the solution here, but it doesn't necessarily show all the steps. So a bit more detailed, you'll find a paper here in Aquarius project in the resources documents. So solution of geometric Brownian motion SDE. I'm not going to give the details here. You can read it yourself if you're interested, but it starts again at the differential equation, a bit more introduction, and why in the end we get this solution. So there's a slight difference between these two formulas, and we are going to study them next. So we configure the software to run this study job, which will start this class, and we enable solution of JBM SDE. And what are the parameters? We are going to play a bit with some parameters. So we want to see the difference between these two formulas after, let's say, 1 day or 1 year. What's the difference between using one or the other? So now we start with 1 day. Spot price, it's 100. Spot growth rate, it's 5% per year. Stock volatility, it's 35% per year. And how are we going to generate the distribution of the stock prices at maturity? We are going to use a technique called inversion of the cumulative distribution function. So people are more familiar with the probability density function, like the bell curve. So let's say we have a normally distributed random variable, and a standard normal would take values positive or negative around 0. So at the point 0, it's the most probable, the most dense amount of times when this variable appears. And as we move away from 0, it appears less and less. So another way of expressing this is through probability. So the idea is how probable is that a variable will be less than a certain amount. So let's say -5. Well, the probability of a standard normal variable less than 5 is pretty much 0. What's the probability that it will be less than 0? Well, it's exactly 50%. So 50% of the normal variables will be lower and 50% will be higher. So it's just another way of expressing the same thing. But this one is interesting because we can do the following. We can take probabilities between 0 and 1, which is exactly what we are doing here. So go between 0 and 1 with any granularity we want, like 100,000 points, and generate. So we have a probability between 0 and 1. Okay, and for probability 0, what would be the probability density function that is equivalent to this? No, what would be the, okay, what is the so essentially this, we have the probability, and now we generate the x. So what is the x which corresponds to a probability of 0? So something around -5. What's the x that corresponds to probability of 0.5? Well, it's x is 0. So we have this inverse cumulative probability function, which is provided by some math package. And in this way, we generate in a deterministic way the values of the random variable z. I've denoted here. Okay. So we have the random variable, and we're going to use both formulas. So one of them, formula 1, it's the differential equation formula. So spot at sometime in the future equals current spot plus the current spot multiplied by this thing. So mu times t plus sigma or times, and this differential of Wiener process, it's actually this thing which is discussed in this paper. So square root of time times this random variable. That's why we need it. So that's the first formula. And the actual solution, it's the second formula. So we are using this. So spot times exponential of mu minus sigma squared over 2 times t and all this formula. And we're going to, let's run it for one day. So see what we got. Okay, so we run it for 1 day. Look in the, okay, and we have generated the z's. So several, let's see how this z variable looks like. It should be a normal distribution. So I've created a histogram of it, and if we look at it, insert chart, well, it's a perfect normal distribution. So we have generated the standard normal just fine. And now we are going to look at the first forwards and the second forwards. First forwards are generated using the differential equation, like this. So between, let's say, 85 and 115. And the second forwards, well, they seem pretty much the same thing. Well, if I'm looking at these two, there doesn't seem to be much of a difference. So maybe slightly shifted, but not by much. So let's look at them overlapped. Plotted both on the same chart. And again, they seem to be pretty much overlapping. So this is actually kind of true. So for small values of time, the solution of the SD or the differential equation give pretty much the same values. Now, what if we increase the time from, let's say, differential time 1 day to a lot bigger than 1 day, so 252 times bigger. Now, if you run the program again, okay, let's look at the first. And what we notice is that we get negative prices. So with the differential formula, the price can become negative, which obviously cannot happen because the price of a stock cannot be less than 0. So that's the problem with one of the problems with the differential formula applied for non-differential time. And let's look at the exponential formula. Well, we notice that it doesn't become less than 0. And also the appearance of the plot, it's skewed. So it's no longer normal, it's so-called log normal distribution. If we plot them on the same scale, let's insert chart. Well, they don't look that well, but see. Okay, it's more clear. So the differential formula gives a normal distribution at any time, which isn't true. It's only normal for very small differential time, and for large time it's log normal, so it looks a bit more skewed like this. And the problem with the normal distribution is that the price can become negative, while in the exponential formula, so the actual solution, the correct solution, the price can never become 0. So in conclusion, for simulation, we are going to use this formula, so the exponential version. And it's not wrong to use it for small time as well. So even for 1 day, they give, this is more accurate, because what is the differential time? It's 1 day, or it's a tenth of a day, or a millionth of a day. So best thing is to use the closed form solution if you have it. Otherwise, if you don't have the closed form solution, then you need to use the differential formula. And when you have some larger time, then do simulation. So split that big time into smaller chunks and use the differential formula for each of the smaller chunks. But if you have directly the solution, it's faster and more accurate to use it. So this was the conclusion for now. So having introduced a way to compute the stock prices, the distribution of the stock prices somewhere in the future, let's call it maturity, because we're going to use that for options. We are ready to start calculating the price of an option. So let's switch to option pricing study job. And we do initially the same, essentially do the same thing as for JBM motion study job. So we generate probabilities in order to generate forwards. And let's see how those forwards look like. So we are starting at some spot price, 100. Have a stock movement with these parameters: growth 0, volatility 25%, maturity 20 days per, when the year has 252. There seems to be a bug in IntelliJ. It doesn't show this stuff. Great. And let's look at how forwards look. So the forwards at 1 month are relatively normally distributed. Actually, they are log normal. So they are a distribution of, they have a certain, so there are more of them around 100, a few less than 100, more, a few higher than 100. So essentially, for each of these prices, we have an option contract, which we can choose. We're choosing it to be a call option. The strike price, which we choose to be 100, and a call option will be worth as much as the stock is exceeding the strike price. So for any stock price that's higher than 100, let's say the stock price is 120. In that case, the call option will be worth 20. If the forward price, so after 1 month, we have the stock dropping to 60. Well, in that case, the call option is worth 0. So it's not, if you would have hold the stock, would have lost $40. But because we hold an option, a call option is just, that option is just worth 0. So at that point, for any price below 100, the option is worth 0. And for any price above 100, it's worth the difference. This is a more elaborate formula for calculating the option price, depending on whether it's a call or a put, because there is also put options, and put options are opposite to call options. So they are worth something when the price is dropping and 0 when the price is increasing. But for now, we are just going to use a call option. Okay, so we are generating the forward prices and calculating the option value for each of the forward prices. So let's look at how those values also look in a plot. So the values. Okay, so like this. Well, the vast majority of the values of the options are 0 because about half of the prices of the stock at maturity will be below the strike price. So in that case, the price of the option is 0. And as the price increases, they will be worth more and more, but with fewer probability. So it's this distribution of probability, an exponential sort of. Okay. And as we know from probability theory, when you have a random event and you're betting on that, well, the worth of that event is the average value. So we have various values of the option, most of them 0, some not 0. And what is the average value of those bets? So let's say we would, what is the average value of that option? So that option, let's look. Okay, so the simulated value, we'll get back to the Black-Scholes value soon. So actually, these are the values. So the mean value is actually 2.81. So if you would calculate the average value of all these options at maturity, you would get 2.81. The minimum value is 0, and the maximum value is 63 something. So this would be the average. And what is the Black-Scholes theoretical value? We'll get to that soon. But let's just calculate it here. So the Black-Scholes value is a way of calculating it directly using a closed formula. So we are just going to input the same parameters as in the so-called Monte Carlo simulation. So stock price 100, strike price 100, no interest on dividend, like we have here 0, 0, volatility 25%. And it's important to equivalent the times. So times have different conventions. On this side, they are using 365 days a year. I'm using 252 days a year. So since I'm using 20 days out of 252, so let's divide 20 like this. This is the ratio of a year that I'm using. This is the year fraction, and I multiply this by 365, and I'm getting this number. So I have to input this exact number of days in order to have the exact same definition for my option. So with this definition, you can see that the actual theoretical price, it's the same as calculated by your statistics. So by averaging the option values among all the possible stock values at expiry. And I also have this calculation directly. So using the Black-Scholes formula, and if I'm logging that, I get just like this website. So the Black-Scholes price is 2.81. The statistical average price calculated using a statistical simulation is again 2.81. And it's also worth looking at the P&L, so-called profit and loss. So, okay, the average option under this market parameters, the average option price would be 2.81. But this means that probably, most likely, the market will sell us the option at 2.81 if you want to buy it. If you want to sell it, we'll probably need to sell it around this price also. So what we are going to do, so at the beginning of so we have a transaction where we are buying the option at the beginning. So let's say now, and we are selling the option after maturity, so after 1 month, and the profit or the loss from that transaction is this. So we are paying money now, so let's minus, and the price now is the theoretical value or the Black-Scholes value. So the current price is 2.81. And at maturity, we are going to, so we bought it, we lost this money, and then we are going to sell it. So then we win this amount of money, which is the amount of value of the option. Sometimes we win 0, sometimes we win, I don't know, 40. So this is the P&L. We are also plotting the P&Ls, and the P&L should be 0 on average because we are buying at average price, and eventually are going to also realize the average price. So let's look how the P&Ls look. Okay. Set chart. Well, predictably, it looks a lot like the option prices. So since we buy the option at its theoretical value, and most of the times the price at maturity is 0, we are just going to lose 2.8. So most of the times we are actually losing 2.8 when we as profit and loss. And sometimes we make some money. And if we look at the P&L statistics, the mean is 0. So on average, we are not making money, we are not losing money. But the minimum amount of money that we can lose, it's the price that we paid for the option. So we cannot lose more money than we paid for that option. When the stock price drops significantly, the option is just going to be worth 0, and we paid 2.81 for it, so we are losing all those money, but not more. So let's say the stock is 100 and drops to 50. Well, if we buy a call, we are just going to lose the PV, $2.8. But if the option, let's say, doubles, we are going to make the difference, so another $100. So this is how the distribution of the profits looks like, and actually it's not that great. It's pretty lousy, actually, because most of the times we are losing money, and generally we don't like this sort of bets. Like we would like to be more reliable, not most of the times lose, and sometimes win a lot. It's fine to win a lot, but not to lose on most occasions. So in the next part, this chapter, we are going to look at how we can improve this distribution of the P&L, and we are going to do that by resorting to the Black-Scholes way of pricing options.